In order for us to understand how digital systems manipulate data, we must know the operation of binary addition, binary subtraction, binary multiplication, and binary division. Let's start with binary addition. And let's try to add different binary numbers until we exhaust all combinations of single-bit binary numbers. But since we are familiar with the decimal number system, we will add the binary number side by side with its decimal counterpart. The first combination we would like to examine is bit 0 plus bit 0. The operation binary addition, when it comes to physical digital circuit, is closely related to the OR operation. So I can read this as 0 or 0 or bit 0 or bit 0. And this results to a binary 0. In decimal number system, decimal 0 plus decimal 0 equals decimal 0. How about bit 0 plus bit 1? Based on OR operation, 0 plus 1 has a sum of 1 with a carry of 0. In decimal number system, decimal 0 plus decimal 1 equals decimal 1. How about bit 1 plus bit 0? Based on OR operation, 1 plus 0 has a sum of 1 with a carry of 0. In decimal number system, decimal 1 plus decimal 0 is equal to decimal 1. Finally, the bit combination we are supposed to explore is bit 1 plus bit 1. Before we write down its sum and carry, let's look at its decimal counterpart. In decimal number system, decimal 1 plus decimal 1 is equal to decimal 2. However, in binary number system, this decimal number 2 is represented by 1, 0. Therefore, when bit 1 is added to bit 1, the result can be read as 1 plus 1 equals a sum of 0 with a carry of 1. So again, this is the sum and this is the carry. Now the bit that contains the carry part is called the carry bit. This combination is very similar to the truth table of the OR gate. As an example, let's try to add the binary number 101 to binary number 11. 1 plus 1 is equal to 0 with a carry of 1. Next, 1 plus 1 is equal to 0 with a carry of 1. Finally, 1 plus 1 is equal to 0 with a carry of 1, which I will directly write in this leftmost bit. So this is our final answer. Let's try to convert the addends into decimal form and also the final answer to verify if our answer is correct. So if this is the least significant bit and this is the next significant bit, this is the third bit and this is the fourth bit, this position has a weight of 2 raised to 0. This one has a weight of 2 raised to 1. This position has a weight of 2 raised to 2 and this position has a weight of 2 raised to 3. 2 raised to 0 is 1, 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to 3 is 8. So 101 is 4 plus 1, which is equal to 5. Next addend is 1. So this is equivalent to 2 plus 1 based on these weights. So this is equal to 3. Next, our answer is 1000. So based on these weights, the non-zero part is multiplied to 8. Hence, this is 8, which tells us that our final answer is consistent when the addends are converted into the decimal number system. Our answer here is correct. When performing binary subtraction, we must remind ourselves that when bit 1 is subtracted from bit 0, a borrow is required from a higher bit position. To illustrate this point, bit 0 minus bit 0 is equal to bit 0. However, bit 0 minus bit 1 requires bit 0 to borrow a binary value 1 from a higher bit position. If it cannot borrow from a higher bit position, then this operation will not push through. The process will simply stop. However, let's assume that this bit 0 can freely borrow another bit so that we can write this as 1, 0. So let's just assume that there's another bit position here where this 0 can borrow a 1. Now we have a binary number 10 which has a decimal weight of 2 and a binary number of 1 which has a decimal weight of 1. So 2 minus 1 is equal to decimal 1 or equivalently bit 1. Next, bit 1 minus bit 0, this is equal to bit 1. And bit 1 minus bit 1 equals 0. For those who are familiar with logic gates, these combinations are the same with the truth table of an exclusive or an XOR gate. Therefore, we can perform binary subtraction on 2 bits by applying the XOR operation. As an example, let's try to subtract the binary number 1101 with the binary number 0110. So let's begin with this pair. 1 minus 0 is equal to 1. 0 minus 1. So here we need to borrow 1 from the next higher bit position. So this becomes 1, 0 and this becomes 0. 1, 0 minus 1 is equal to 1. Next, 0 minus 1, we need to borrow from the next higher bit position. So this becomes 0 and this becomes 1, 0. 1, 0 minus 1 is equal to 1 and 0 minus 0 is equal to 0. So let's try to check if our answer is correct by converting this to decimal and this number to decimal and this number to decimal. So let me try to write the different bit positions. This is the least significant bit and this is the next bit. This is the third bit and this is the most significant bit. This bit position has a binary weight of 2 raised to 0 and this one 2 raised to 1 and this one is 2 raised to 2 and this one is 2 raised to 3. So in decimal form, this is 1 and this is 2, this is 4, this is 8. So let's try to convert this into decimal. So based on these weights, we have 8 plus 4 plus 1. So this is equal to 13. Next, let's try to write down this number. So 0110. Based on these weights, this is equivalent to 4 plus 2, which is equal to 6. For our final answer, we have 0111. Using these weights, we have 4 plus 2 plus 1, which is equal to 7. So let's check. 13 minus 6 is equal to 7. So our final answer here is correct. Binary multiplication is similar to multiplying integers with values 0 or 1. For example, bit 0 times bit 0 is equal to bit 0. Bit 0 times bit 1 This is equal to bit 0. Another combination is bit 1 times bit 0 is equal to bit 0. And finally, bit 1 times bit 1, this is equal to bit 1. So note that this combination is similar to the truth table of an AND gate. In fact, binary multiplication is equivalent to an AND operation. As an example, let's multiply the binary number 1101 with the binary number 101. Let's focus on this first bit in this multiplier. So when you multiply with 1, obviously, you just have to rewrite everything. For example, 1 times 1, this is 1. 1 times 0, 0. 1 times 1, 1. 1 times 1, 1. So basically, I've just rewritten this here. Now, for the next bit, 0 times 1, 0 times 0, 0 times 1, 0 times 1. So I'll just write 4 bits of 0 here. 0, 0, 0, 0. Next, for this bit, just have to rewrite the multiplicand. We have 1, 0, 1, 1. Then add all these partial products. So this is 1. 0 plus 0 is 0. 1 plus 0 is 1. 1 plus 1 is 0, 1. 1 plus 1 is 0, 1. 1 plus 1 is 0, 1. And finally, 1 plus 1 is 0, 1. I'll directly write this to the highest bit position, which is 1. Let's check if our answer is correct. So 1, 1, 0, 1. 2 raised to 0. This one is 2 raised to 1, 2 raised to 2, 2 raised to 3. So basically, we have this non-zero term. So this is equal to 1, and this is our another non-zero term. This is 4, then this is 8. So 8 plus 4 plus 1, this is equal to 13. Let's convert this to decimal form. 1, 0, 1. This has a weight of 1, and this one has a weight of 4. So 4 plus 1 is equal to 5. So we have 13 times 5. 5 times 3, 15. 5, 5, 65. So let's see if our final answer is equivalent to 65. So this has a weight of 2 raised to 0. This one, 2 raised to 1. 2 raised to 2. 2 raised to 3. 2 raised to 4. 2 raised to 5, 2 raised to 6. 64 plus 1 is equal to 65. So these two values are equal, which tells us that our final answer is correct. Binary division is similar to the rules applied in the decimal number system. For example, bit 0 divided by bit 0, this operation, division by 0, is not allowed, or this is meaningless, or this is undefined. Next, bit 0 divided by bit 1, this is equal to 0. Next, bit 1 divided by bit 0, this is also not allowed, or this is meaningless, or this is undefined. Finally, we have bit 1 divided by bit 1. This is equal to bit 1. When dividing binary numbers with more than one bit, we follow the same procedure of long division method. So for example, divide the binary number 0110, 0100 by the binary number 100. The first step is to remove all zeros in the most significant bit of both dividend and divisor. Hence, since our dividend has a 0 on its most significant bit, we can remove this because it will not affect the overall weight of the number. So let's rewrite these two numbers in a more familiar form. So So when we perform longhand division, this is our dividend. We immediately drop this 0 in the most significant bit because it will not affect the overall weight of the binary number. So I'm going to write 1, 1, 0, 0, 1, 0, 0. So our divisor is 1, 0, 0. Now 1 divided by these 3 bits is not enough, so we write down 0 here. Also 1, 1, 2 bits divided by 3 bits is not enough, so we will put 0 here. Next, 1, 1, 0, the combination of these 3 bits is now larger than this one, so I can now write 1 here. So 1 times 1, 0, 0 here, and then subtract. I'll end up with 0 minus 0 is 0, 1 minus 0 is 1, and 1 minus 1 is 0, but I don't need to write it here. Next, write the next bit here. 1, 0, 0 divided by 1, 0, 0. This is obviously 1. 1 times 1, 0, 0. This is equal to 0. So I'll drop this one. This value here is less than 1, 0, 0. So I'll put 0 here. Next, I'll drop this one here. 0. So 1, 0 is still less than 1, 0, 0. So I'm going to put 0 here. And let me drop this one. 0. 1, 0, 0 divided by 1, 0, 0 is obviously 1. When the most significant bit is 0, we can drop this portion. So we now turn to the next significant bit, and this is still a 0, so we can also drop this part. Therefore, our final answer is 11001. So let's check if our answer is correct. So I'm going to skip the part where I convert this to decimal and this one to decimal and this one to decimal. I'm just going to directly write it here to save time. You can do it on your own. This first number is equal to the decimal 100, and this one is equal to the decimal 4, and this one is equal to the decimal number 25. So based on our initial values, 100 divided by 4 is equal to 25. Hence, our final answer is correct. Don't forget to like this video, subscribe to my YouTube channel, and hit the notification bell button for awesome updates. Thank you for watching.